Good day, everybody. This is EEE 201 or ECE 200 Electrical Circuit 1 class. You are most welcome. Today's topic, we're going to discuss a magnetic circuit. Under magnetic circuit, there are a couple of properties I'd like to discuss. First of all, I'd like to see the magnetic flux lines flow through a magnetic material. For that, I'd like to draw a magnetic transformer where you can see looks like a magnetic core of rectangular size, and is a three-dimensional diagram for this one. It looks like this, and current coil is connected to the primary side. It's like this, and the direction of the current is like this, and the secondary side voltage induced in the coil, that is drawn like this. Okay. Now, due to the current flow into the primary side, flux lines will passing through the magnetic material in this way. So the direction of the flux lines is like this, where the flux lines are denoted by the phi, which is Weber per meter square, and the current flow through the primary we can assume is I, and the cross-section area of the core material we can assume as A. So we know that according to the according to the definition of flux density, we know that the number of lines per unit area is known as a flux density. So if the flux, that means if the flux density is we call B, then that B will be equal to phi by A. That means your Weber per meter square, Weber per meter square, which is denoted by Weber per meter square, or it's also known as Tesla, which is represented by T, or Tesla called. And for instance, if the flux density of this core materials is through this core material is 6 into 10 to the power minus 5 Weber, and the cross-section area of the core material, if you consider 1.2 into 10 to the power minus 3, meter square, if you consider, then the flux density B will be phi by A, which will be 5 into 10 to the power minus 2 Weber per meter square, or 5.5 into 10 to the power minus 2 Tesla. We can say the flux density in this way. The next parameter is going to be considered is the permeability of the core material. The permeability, which is represented by mu. So it depends on the materials of the core. So different core got different permeability. The permeability for the free space or vacuum is considered as permeability 4 pi 10 to the power minus 7 for vacuum or any free space. This is the permeability, and Weber per, the unit is Weber per ampere meter. And the relative permeability by definition is the ratio to the permeability of the core material divided by the absolute permeability or the vacuum permeability. The next parameter of the magnetic circuit is the reluctance. The reluctance is represented this way, the symbolic representation of the reluctance, and it is similar to the resistance in electrical circuit. So we know that in resistance electric circuit, the resistance R is equal to rho L by A. Similar to that, reluctance in magnetic circuit is the obstruction of the magnetic flux lines through the materials, and that property is known as reluctance. So the reluctance, according to the resistance, it is represented by L by mu A, where L is the length of the materials, core materials or magnetic flux lines, and mu is the permeability, A is the area. So this is the representation of the reluctance in magnetic circuit, which is similar to the resistance of electrical circuit. This leads us to the electrical circuit Ohm's law, as a magnetic circuit Ohm's law, where we know that in electrical circuit Ohm's law, the current equal to voltage divided by resistance. So similar to that, in the magnetic circuit, the current, which is similar to the flux line, equal to the magnetic motive force divided by the reluctance. The magnetic motive force, which is very similar to the voltage in electrical circuit, by definition the magnetic motive force in magnetic circuit is equal to N times I, where N is the number of turn and times I is the current through the coil. Like if we look back to our circuit here, this is the current I, and N, if we consider here, is the number of turn around the coil. That's Ni. F will be equal to this magnetic motive force will be equal to this N into I. That's the input voltage we can consider as well. This is the magnetic motive force in magnetic circuit. Now if we draw the magnetic circuit, it looks like the magnetic motive force, which is like the voltage source, then the reluctance, which is look like the resistance connected to this circuit, and this is the reluctance we can call, and the current flow through this is the phi through the circuit. Then we can say that according to the Ohm's law, is voltage or magnetic force divided by reluctance, or we can say Ni by reluctance. This is what we can say. The next property we'll discuss, the magnetizing force. Magnetizing force which is represented by H. So by definition, it is the magnetomotive force per unit length. So by definition we can say this is the unit force, the magnetomotive force per unit length, where L is the length of the magnetic flux line. For example, if we say that this is a core material, or it's a core, circular core, and a current coil is connected here like this, okay, and the flux lines are in this direction phi, and then this, the length of this flux line flow is L. Now let us assume that the current I, and this is the number of turn N and L. Now if the current flow through the coil, through the wire is 0.1 amps, and the number of turn of the coil is 400 turn, and the length of the flux line L equal to 0.2 meter, then the magnetizing force will be H equal to F by L by definition, equal to Ni by L, which will be equal to, the N is 400 times I 0.1 divided by 0.2, and that gives us 200 ampere turn per meter. The unit is ampere turn per meter. So that's what we can get, the magnetizing force for this particular. Now we are going to discuss the most important properties. There's a relationship between the magnetic flux and the magnetizing force. That is the relationship between B and H, which form the BH curve ultimately. So we know that the relationship from the magnetizing force, which is equal to Ni by L, where if you see that if the current of the coil increased, then the magnetizing force also increased because they are proportional, and this current I is increasing the current is increasing the flux lines. The more the current increase, the more the flux lines increasing, and we know that the flux lines is equal to we know that this flux density is equal to this flux by area. So with the increasing of the phi, the flux density also increasing. So we can say that with the increasing of I, which increase the magnetizing force, and increasing I, increasing the flux lines, and flux lines increasing the flux density. So ultimately the flux density and this flux, the magnetizing force, are going to be proportional to each other. That's what we say. because with the increasing of current, the H increasing at the same time, we are seeing that the B is increasing. So with the increasing of H, ultimately we can say that the B is also increasing. These are proportional to each other. That's what we can say. So your B is proportional to H. In that case, if we start the graph from the center, initially there is no current, so no magnetization, so everything is zero. And then the increasing of current, the H increasing, hence the B is increasing, and B is increasing, goes to saturation at a saturation point over here. This is the knee saturation or knee point. This is the way the relationship gone. And also same way, a reverse way, if the current decrease, the H decrease, and ultimately the B is decreasing, because everything is decreasing, so your B is decreasing. So we can say that with the decreasing from here, with the decreasing of H, the B is decreasing. But the interesting thing is that it is not following the same path. Rather, at the time of decreasing, it follows the different path like this. And you're decreasing some more, it goes like this. And again, goes to the negative saturation. And if you go from here, again increasing the magnetic flux line, so then again it is increasing, the current is increasing, at a different path it follows and goes back to the saturation again here. So this is a complete cycle called Carnot cycle, or this loop is called hysteresis loop. This hysteresis loss is coming from the area under this hysteresis loop. So this is the way actually the BH relationship occurs. Now our target is not here, all these things, rather we will see only the part which is this part for the BH curve, the blue part. From here to here, for each of the materials, if we go, then we will see that different BH paths it follows. Okay, here is an example of a BH curve. If you can see, there are three different materials. One is your cast iron, another one is your cast steel, another one is your steel sheet. And these three different materials core having three different BH curve, and the cast iron BH curve is this one, and this is the BH curve for the cast steel, this is the BH curve for the steel sheet. So different BH curve for different core materials, that's what we can see. So what it happens here, actually starting from zero and the BH curve's gone to the saturation until that. Now if you go back, it comes to the different and then go down like that way. Again, this is the same thing. If you go back, it's coming with backward direction in the different path. Again, if you go this, it can go with the different path. So this is what we can see the BH curve example for different material. Now if we look carefully, the coordinate of the BH curve, the H in this direction, and this is the H direction, and this is the B direction. The values of H are given here in ampere turn. 0, 300, 600, 900 like that are in ampere turn, and 0.2, 0.4, 0.5, these are given in Tesla. So this is the way actually the scaling is done for this curve. Now we are going to use this BH curve for different core materials in different problem solution. Let us solve a problem first. In this circular core problem, we can see that the number of turn for the primary side is a 400 turn, and the current flow through I phi is the flux lines. The area is 2 × 10⁻³ The material is made of cast steel core. The flux line path is the 0.16 meter. Now we have to find what is the current flow through this coil so that we can get the flux lines phi is 4 × 10 to the power minus 4 Weber. That's what we have to find first, and then we have to find the permeability and the relative permeability of this material. If we want to solve this problem, first we have to draw the equivalent circuit, equivalent magnetic circuit, which is like the magnetic force we can apply. I'm talking about the solution to the problem. If we draw the equivalent circuit, the magnetic force and the and the reluctance, and then this is your phi, this is the reluctance, and this is the, actually this is what do you call that, the magnetic force F. Now this is the circuit we can have, the magnetic circuit we can have, but for the solution first we have to find the flux density B equal to, you know that B equal to phi by A, and then the value of phi by A will be, if you substitute the value of phi, which is into 10 to the power minus 4, and A, the area was 2 × 10 to the power minus 3 we had. So we are going to get the value is 0.2 Tesla. 0.2 Tesla is the value of the flux density. Now we need to find the I. So we know that the magnetizing force equal to Ni by L. So from here we can get the value of I from here, like HL divided by N. Now we got the value of I, L, we have the value of L, we have the value of N, only the H we need. But we got the value of B, so we have to find the value of H from B, and that one we have to get from the curve. This value of H we can find from B through the BH curve, because that is we know that locally it is very much you go to the BH curve, this BH curve. But what is the material? First we have to look. The material is a cast steel core. So cast steel core, if you go for cast steel core, then the cast steel is this one, that is this, the middle one. This is the cast steel curve. So we have to follow the cast steel curve, and what is the value of B? We can see the B is this, and this is B, and this is H. So we got B equal to 0.2 Tesla. So we have to find the corresponding H. Look, go to that 0.2 Tesla is here. 0.2 Tesla. 0.2 Tesla is here, and the corresponding what do you call that? Corresponding value of H, if you go to the middle curve, then this is giving you this value, almost intersecting here. So the corresponding value is coming here, somewhere here, which may be 150. So we can consider as a 150 value. If you consider this is 150 or 170 or whatever, let's say 170 we can consider, and then we get this value as 170, or approximate value, whatever it is, 150 or 170, doesn't matter, whatever it's close to this is alright. So if we get 170, then H value we can write, and 170 ampere turn from the what do you call that, turn per meter. Ampere turn per meter. We can write ampere turn per meter. Okay, this is our H value we are getting from the BH curve, and then we can substitute this H value 170, and L is not L squared, it's L. The L value is coming here as if you go back, the L is giving here 0.16, 0.16, and N value is given here something like 400, or if you go back again in the problem, N value is given here around over here is a 400. So if you substitute 400 here, then you are going to get the final answer, which is 68 milliampere. So this is our answer. The current actually need to flow at the 68 milliampere in order to get the flux density or flux lines 4 into 10 to the minus 4. The second part is the determination of mu. We have the equation that mu equal to B by H. So we can find from the B and the H, we can find the value. B is 0.2 Tesla and H is 170. We are getting the value as 1.176 into 10 to the power minus 3 Weber per ampere meter. Okay, that's what we are getting here for mu, and the mu naught and the mu are the relative permeability, which is giving mu naught, as I told, this 1.176 10 to the power minus 3, and the mu naught in the free air, the mu naught is 4 pi 10 to the power minus 7. We can put there, and then we can have the value is 935.83. So that's the relative permeability. Okay, let's go for the second problem. If you see the second problem, in this case the electromagnetic figure has picked up a section of cast iron, and you have determined the current I in the primary coil to establish the indicated flux code, that is phi equal to 3.5 10 to the minus 5 Weber we can get. So for what current we are getting this phi, that's what we have to determine from here. And you can see in this example, this core is divided into two parts. The upper part is made of steel sheet, lower part is made of cast iron. And the number of turn of the coil is 50 turn. The current is going through this way. The phi things is there. The most important thing you have to look here is the indication is the A, B, C, D, E, F. These are the 4 points. The flux path is shown by indicating this: A to B, B to C to E to F, like that way the flux lines are passing through. So the length we are going to consider here, and its length given here 4 inch from here to here, square LABC, like that. If you see, it is given accordingly. So LABCDEF and FA 4 inch is, and LBC LD is 0.5 inch. I convert the inch into meter, and the cross-sectional area of the chord throughout is 1 inch square. This has to convert into MK system in a meter. That's what we have to do. Now let's see how to solve this problem. First of all, we have to think one thing, that there are two types of materials combined together. It's a steel sheet and cast iron. The lower part is cast iron, the upper part is steel sheet. So the applied magnetomotive force is going to be applicable on these two separate iron core. That's why we have to go for let's go to the next section of my video, presentation, how to get the solution of this problem. Thank you.